Hello and welcome to section 5.2, which is on perpendicular and angle bisectors. Equidistant means being the same distance from two objects. And so that gets us into a couple of theorems that we're going to use for this section. Theorem 5.2, perpendicular bisector theorem. If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. And that would make sense, since the perpendicular bisector cuts something in half. A point on that bisector then would have to be the same distance from the endpoints. Theorem 5.3, the converse of the perpendicular bisector theorem, so the opposite, in other words. So now we know that a point is equidistant from the endpoints, then it has to be on the perpendicular bisector. So it's the opposite of what I just said. The converse. What is the length of QR in my example? So Q to R is here. Because I know that these two are equal, and these are 90-degree triangles here. So since I know PS is equal to PR, QS has to be the perpendicular bisector then. And because it is, that makes QR and QP equal to each other. And because you know that, you can do the work then to figure that out. So you set them equal to each other. I didn't really leave myself a room here, so hang on a second. Okay, so I have set these two things equal to each other, the QP and the QR. So 3n minus 1 equals 5n minus 7. And then I'm going to subtract 3n from here and move it to this side. Leaves me with 2n, and I will add 7 and move it over here. Negative 1 plus 7 is 6, so 6 equals 2n. Divide by 2 to get rid of it, so n equals 3. That's not my final answer though, because I need to plug it back in. I want to know how far is it right here from Q to R. So plug it in. 5 times 3 minus 7, 5 times 3 is 15, 15 minus 7 is 8, so 8 equals Q to R. 8 would also equal Q to P, because they would have to be equal if it's equidistant. So then the distance from a point to a line is exactly what it sounds like it would be, the length of the perpendicular segment from the point to the line. So in other words, the length of the shortest segment from the point to the line. Theorem 5.4, which is the angle bisector theorem. If a point is on the bisector of an angle, and the point is equidistant from the sides of the angles. Okay, so before we were talking about the perpendicular bisector theorem. Now this is the angle bisector. So you're cutting an angle in half this time. So the point would be equidistant from the sides of the angles. And that would make sense. If you're cutting right through the middle of it, it would have to be halfway between. Theorem 5.5, the converse of the angle bisector theorem. So again, converse means opposite, basically, of what you just said. So if a point in the interior of an angle, the inside, is equidistant, so the same distance from the sides of the angle, then you know that that point is on the angle bisector. It would have to be an even amount from both sides, an equal amount. So in my example here, I have a drawing, and then I want you to find the length of FB. And this is F right here. It's kind of hard to read, but that's F. So F to B is what you're trying to find. So if I know that I have these right angles drawn right here, and right here, and I'm showing you that this one equals this one, okay? So then I know that C to B and C to D and C to B would be equal, and so that's where I can start. To figure this out. The 6x plus 3 is from here to here. I wrote it over here. I should have wrote it here. should have wrote it in here, but it was kind of hard to do. Okay. So then if I know that those two things are equal to each other, they have to be, because I bisected the angle. 6x plus 3 equals 4x minus 9. I just go through here and solve this. So I'm going to go minus 4x, get rid of it, move it over here. That leaves me with 2x minus 3, get it over here. Negative 9 minus another 3 would be minus 12. And then go ahead and your last step is to divide by 2. Your x would then be this should have been, let's see. Hang on one second. So this should have been a plus 9 right here, and I wrote it incorrectly. This should be plus 9. So if I have a plus 9 and a minus 3, I end up with 6. And 6 divided by 2 is 3. Once I find that that is 3, I can plug it in. So 6 times 3 is 18. And then you still have the plus 3 here for the other part of it. So 21 equals B to F, or F to B, same thing. So the last thing that I have here is to prove the converse of the perpendicular bisector theorem. So given information is that PA equals PB, with PM being perpendicular to AB at point M, and I have drawn the picture right here to go with it. And then I want to prove that P is on the perpendicular bisector of AB. So let's bring this down here. So I have the statements given, and we need to go through here and figure out what it is we're using for our reasoning. So if I know that PA is congruent to PB, which that was given information, so this side equals this side, and then angle AMP is congruent to angle BMP. How do I know that? Because all right angles are equal. Or definition of a right angle, you could say that too. So then PM is congruent to PM. Well, which property is that that says that? It's the reflexive property that says something is equal to itself. Why do I need to know that PM is congruent to PM? Because I'm trying to prove that the sides of the triangles are equal. So triangle PMA, the one on the left, right here, is congruent to triangle PMB. So now I can use the hypotenuse leg theorem to prove that. I proved that one leg here and here and the hypotenuse were equal. So AM is congruent to BM. And what am I going to use there? It's not really a theorem, but it's a thought process that corresponding parts of congruent triangles are equal, are congruent. So PM is perpendicular bisector of AB. I can just say by the definition of perpendicular bisector to prove that. Okay, so bring that knowledge with you, and we will talk about it more the next time I see you. Have a good night.